ओके सो आज के ट्यूटोरियल में हम लोग डिस्कस करेंगे राबी हैमिल्टोनियन की ट्रांसफॉर्मेशन किसी रोटेटिंग फ्रेम के लिए और एंड दिस इज आल्सो कॉल्ड एज रोटेटिंग वेव अप्रॉक्सीमेशन और इन शॉर्ट और डब्ल्यू ए there are a number of ways to transform Rabi Hamiltonian onto a rotating frame, but we will use a very familiar method to employ a unitary transformations to Schrodinger wave equation and then solve the differential equation. Okay, so let's see what we have to do. Okay, so let's apply um, the unitary operator u dagger to psi. So it seems like that we are doing it in a reverse way. Usually we apply a u to a state cat, but this is a sort of reverse engineering that we are gonna do. So okay, so let's so here's the Schrodinger wave equation, the familiar version of the equation. H psi so iota h bar partial or partial times t. Apply this u dagger to this psi, and here we have h dagger psi. Okay, apply the product rule and we will get iota h bar partial u dagger over partial t psi plus iota h bar u dagger partial over partial t psi h u dagger inside. This is as it is. Okay, so rearrange and we'll get iota h bar partial over partial t psi psi minus iota h bar partial u dagger over partial t psi act u on both sides, and we will see that since u dagger equals one or the identity operator, so we'll get iota h bar partial over partial t psi u h u dagger, we put hats over here, minus iota h bar u partial u dagger over partial t and psi. And this certainly looks like I'm Schrodinger wave equation. So so I can write so I can define this term as h tilde, the Hamiltonian in the rotating frame. Um, okay, so let's simplify this Hamiltonian a little. Since u dagger equals identity operator or one, just that's just a number in scale terms. So u partial u dagger over partial t plus u dagger partial u over partial t equals 0. So which means that um, u partial u dagger over partial t equals minus u dagger partial u by partial t. Okay, so this equation becomes partial u by partial t u dagger, and let me call this equation A. So basically we have to calculate this Hamiltonian, and this will be the transformed Rabi Hamiltonian for a rotating wave, and this will give us the rotating wave approximation for the Rabi Hamiltonian. Okay, so let's start by writing Rabi Hamiltonian. Um, Usually the Rabi Hamiltonian can be written as by ignoring the term due to radiation. Um, so this is Ha for atom plus Ha, that is atom. This is interaction Hamiltonian. Okay, and there's also another term due to light, but since we are ignoring this term, ignore since there are very large number of photons, and for a large number of photons, that is for a very big so since HL becomes a number, so in that case we can treat this Hamiltonian as a classical Hamiltonian, and HL becomes just a number, so it doesn't remain an operator. And in the time evolution of Hamiltonian, this number will just lead to the phase shift, and it will disappear when taking the modular square. So it is quite obvious to discard it. So, and we'll just left off with A atom plus H air. So this is my equation number 2. The Hamiltonian for the free atom is H A plus H bar omega B A B B, and this term is also equal to, in terms of polymatrices, so this is also equal to sigma z plus over 2 in a more familiar notation, H bar omega. So this, let me call this equation number 3. And the atom light interacting Hamiltonian is HAN minus polarization vector E naught cos of omega t omega minus plus omega plus. So let me call this equation number 4. So by putting equation number 3 and 4 um, in equation number 2, we will get equation number 2 becomes now minus E naught cos of omega t sigma minus plus sigma plus. So this is equation number 4. So basically we have to transform this onto a rotating frame, and So in general, we have to calculate this term. So let me call this term number 1 and this term number 2. So basically, we have to calculate term number 1. Let's calculate an equation A. So since U unitary operator is exponential, iota omega t iota omega t. Let me. This is my unitary operator, and correspondingly, the U dagger term will just be the term with minus iota. So since this is just a constant, so we can ignore the constant operator. That will yield thing. Ignore the constant operator. Exponential. So this is so let me call this equation number 5 and let me call this equation number 6. Now I can calculate this thing. That is exponential iota omega z by 2 t h bar omega ba by 2 omega z plus 1 minus omega minus plus omega plus and u dagger. And this is equation number 7. So in this calculation, basically we have to evaluate a term like this. Terms like this. Iota sigma I where omega I either omega minus or omega plus. Okay, so to do this we can use Baker Campbell Hausdorff. It is a famous Cbh theorem or lemma. Basically, it's a lemma, not a theorem exactly. So it states that we have to figure out terms like this: theta a b, and theta is just a constant multiplying with the operator. A b plus theta squared by 2 factorial a a b plus theta 3 by 3 factorial and the series goes on to infinity. Okay, and so basically we need what we need here. So and we need either terms like this sigma z commutated with sigma minus. Basically, we have to calculate these two relations. But it would be better to know what sigma plus and minus are, and that will, and in terms of x and y, so that will be easy to calculate. Okay, and so let me call this equation number 8. Okay, now we know that sigma minus we have defined this way, and sigma plus. Sorry, I always messed with this thing. And it implies that sigma minus plus sigma plus is a plus. Yeah, I'm using we get um, we, we get sigma x, and so basically this is equal to 0 1 1 0. This is just a polymatrix, and similarly we can define sigma y, that is 0 minus iota 0. So using so so basically we can define let me do this over here. Yeah, it's better to do all these calculations here. So we can define sigma minus in terms of x and y, so sigma x minus iota sigma y over 2. So we have the following relations. We can easily compute these following relations. Sigma z minus will just be equal to sigma z 1 by 2 sigma x minus iota sigma y, and this will be 1 by 2 sigma z sigma x minus iota by 2 sigma z sigma y, using the general commutation relation sigma I sigma j 2 iota epsilon naught ij 2 iota permutation operator, permutation symbol, and sigma k. So we'll get to sigma z sigma minus iota sigma y minus sigma x minus, so let's take minus out, sigma x minus iota sigma y. So basically we will have minus 2 sigma minus. Similarly, we can also calculate sigma z sigma positive. So that will just be sigma 2 sigma positive. Okay, so let me let's see. Last equation we named it equation 8. So let me call this equation 9 and this is equation 10. Okay, so by using these two relations, um, we can do the required calculation for the Hamiltonian. Okay, so let's see how we can do this one. So now we have to calculate the term like this: iota z by 2 t sigma positive minus iota sigma z by 2 t. So basically we have to calculate this. So using equation number 8, we can write sigma positive plus iota omega t by 2 sigma z sigma positive plus iota omega t by 2 square over 2 factorial, and so on. Okay, so let's discard all the higher order terms. So it will yield sigma positive plus iota omega t by 2. And that's a very long and nasty calculation, so please bear with me. 2 sigma positive plus iota omega t square by 4 multiplied by 2, and this will just be 2 sigma z sigma positive, and it again yields 2 times sigma positive. So that word will be cancelled out with this 4, and this is 3 dots sigma positive plus iota sigma t sigma positive plus iota omega t square, and the remaining two factor of 2 can be written as 2 factorial and sigma positive. So let's take sigma positive out of all the terms. So this is 1 plus iota omega t plus iota omega t square over 2 factorial. And we can see that this is just the Maclaurin expansion of the exponential vector. So it means that this will just be sigma positive is iota omega t, or or I can write this also as iota and by expanding sigma positive into the basis. So this is my equation number 11. Similarly, we can also calculate the results for sigma minus, and sigma minus will get iota omega sigma z by 2 t sigma minus so let me see if I okay, again I made a serious mistake here. So this is BA. Oh god. And this will be sigma minus iota omega t, or e is to power minus iota omega t. So let me call this equation number 12. It's so we have to put all these results into equation number 7 by putting equations 11, 12 in equation 7. We get the first term, that is U HU dagger minus H bar omega BA minus I'm putting minus here. Should there be a negative sign? So if I'm doing sigma Z and the sigma Z, so this should be positive. Okay, fine. Minus dBA E naught cos of omega t A get A Rabi E minus omega t. I'm just putting the values plus get B bra A iota omega t. We call this equation number 13. So this is the first term of the Hamiltonian that we have to. Oh gosh. Let's do this way. Let's circle it this way. Okay, so however, so this is an equation number A. So now we have to calculate the second term of the Hamiltonian. Okay, so let's do that. Okay, now we have to calculate. Now we will calculate term 2 of equation A, and the term 2 is iota partial U by partial T U dagger iota H bar partial over partial T iota omega sigma Z by 2 T, put this, and minus iota omega sigma Z by 2 T. Let's call this equation number 14. Okay, let's simplify it. Iota H bar iota omega sigma Z by 2 and iota omega sigma Z by 2T minus iota omega sigma Z by 2T, and so this will just be cancelled out to 1 minus iota H bar, sorry, minus H bar omega by 2 and sigma Z by writing this into the basis vectors. So minus H bar omega and this is U dagger partial U by partial T iota H bar. So this is equation number 15. So this is equation number, so basically this is the term 2 of equation A. Okay, so by putting equation number 13 and 15 in equation number A, we get by putting equations 13 and 15 equation A, we get H bar omega BA minus h bar omega. Okay, so this is so then it should be b b, and the second term will be, so basically the first half of the first term will be d omega, sorry, epsilon e naught cos of omega t a b minus iota omega t plus b a. Then finally this is my equation number 16. Oh, this is the required result. So this is the transformed Rabi Hamiltonian onto a rotating frame. Okay, so let's do another topic, and now we'll solve the coupled differential equations to find the dynamics of a two-level atom under the resonant excitation. Okay, so basically what we have to do is we have to solve the coupled differential equations to find the dynamics of the two-level atom under resonant excitation. Okay. So we know that the dynamics of a two-level atom with rotating frame transformation and rotating wave approximation can be given by the following two differential equations. That is lambda partial by partial t Ca Ca tilde t equals minus iota omega by 2 um, Cb tilde t equation number 1 partial by partial t Ca tilde t minus iota omega by 2 Ct plus iota delta Cb t equation number 2, and where Ca t is just equals Cat, and Cb is um, and I can write Cbt as Cb t e raised to power iota omega t, and delta equals omega minus omega b, and these are just definitions. dBA over h bar e naught. Okay. Since we have to deal the atom under resonant excitation, that is um, for resonant excitation, omega BA minus should be equal to omega, that is delta will be 0. Okay, so we have the following versions of the first two equations: partial or partial t Ca T minus iota omega by 2 Cb, and this will remain the same, and this will be changed. Second term will drop to 0. Cb T minus iota omega by 2 number 4. Okay, so let's start from equation number 3. So we have to again differentiate equation number 3 with respect to time. So from equation number 3 we can write partial square by partial t square minus iota omega by 2 partial or partial t Cb of t. So by putting equation number 4, the value of partial t by partial t Cb from equation number 4, we'll get minus iota omega by 2 minus iota omega by 2 Ca t. So that is partial square by partial t square minus omega square by 4 and C of t. This is equation number 5. We can write in a more familiar form, partial square by partial t square Cat plus omega square by 4 is equal to 0. And similarly, using equation number 4, we can write partial square by partial t square Cbt minus omega square by 4 Cbt. This is equation number 7, and or partial square by partial t square Cb t is equal to 0. Now there is a thing. Now we can see a very familiar thing in equation number 6 and 8. These are just the equations of harmonic oscillator. So these, and we know how to solve these equations. And these are just the equations of harmonic oscillator. And their general solution should be like this. Say for example for equation number 8. So this will be like Cb tilde of t A sine omega t by 2 plus B cos omega t by 2, where A and B are constants and they can be found out from the initial conditions. So however, we can, using Cb and Ca, we can write the solution as Cb of t equals Cb of 0 at t is equal to 0. So that's our initial condition. So cos of omega t by 2 minus iota Ca tilde of 0 omega t by 2. So this is equation number 9. Similarly, we can write the solution of for Ca, and Ca of t tilde C of tilde Ca of t equals Ca 0 cos of omega t by 2 minus iota Cb tilde of 0 sine, and this is equation number 7. And we can also see that we can see modulus square of Cb t square plus equal to 1. Okay. Now suppose that we start with an atom in the lower state. So suppose the atom is in, we start with an atom in the lower state, so then Ca of 0 will be 1, while Cb of 0 is equal to 0. So since this is our lowest state and this is our initial state, so atom is in this state. So definitely, so this will correspond to 1, and this will have no atoms. So this condition at t is equal to 0 will just be 0. Okay, so equation number 9 becomes minus iota sine omega t by 2, since Cb of t is equal to Cb tilde of t minus iota omega t. Cb of t equals minus iota omega t sine omega t by 2. Okay, so the probability to find the atom in the excited state is P of b t square sine square omega t by 2. So let me call this equation number 11. Oh, what? I'm making too much equations. I'm designating. So oh, that's fine. Okay, similarly, we can use for equation number 10, using the above conditions, we can write equation number 10 using the same conditions. So Ca tilde t equals cos of omega t by 2, since this just equals to Ca of t. So I think I should put tilde here and not here. So this will just be equal to cos of omega t by 2, and probability to find the atom in this state is equation number 20. And we can also verify that sum of probabilities is yielding to 1. So this is the required result. So basically we have to calculate probabilities. So that's it from this tutorial, and thank you.